All right, in this video, I'm looking at part of 4.8. I just want you to watch the video on the easy part of this, which is getting the differential of a function, because it's really just a matter of notation. The work is going to be just like doing a derivative. You just have to learn this new notation, okay? All right, so this is section 4.8. All right, so this whole next unit we're doing gets at, once you know how to do the derivative, what is it good for? What can you do with it? Okay. So in 4.8, they talk about this concept called a differential. There's a whole portion of calculus that involves solving what they call differential equations. Okay. So all we're doing on this one is in this video is learning about the differential notation. What is it? Okay. All right. So it says, as you see in the box, if we have this y equals some function of x and it's differentiable on an interval containing the variable, the differential of x, that's the dx piece, okay, is just some number, and the differential of y would be denoted dy equals f prime x dx. So it looks like it's hard or some new notation, but really it just comes from this idea, and I just want you to see this. So if we have a function of x, y equals some function of x, we've been taking derivatives, right? And when we write something like dy dx, that's just f prime of x. That's just y prime, right? That's just y prime or f prime of x. We've been doing that. We're familiar with that notation. Let me erase this for a minute. So we're familiar with that notation. Now compare these two. Look at what we did to get from the derivative notation to differential notation. If you look at it, dy over dx, dy divided by dx equals f prime of x. To get to the differential notation, see how they just really multiplied both sides by dx? Okay. So we know that dy equals f prime of x dx. Now these little differentials, the dy and the dx, they wind up being a small change in those variables. And so we'll use this in a minute, with some application problems to get a better sense of why we'd want to do this and how we could how we could think of what dy really is by itself and what is dx really by itself. But for now, just the easy part, I want you to be able to go and rewrite a problem in both take the derivative and use regular derivative notation and then rewrite it in differential notation. Okay. So if we started with y equals 2x squared and we went to find the derivative with respect to x, we could write it y prime, but let's use this other notation. Dy dx would equal 2 times x to the first power, right? So it would just be 4x. We know that. Okay, so dy dx equals 4x. Well, when I come over here to then write this in differential notation, all I'm going to do is bring that dx, multiply both sides by dx, and rewrite it as dy equals 4x dx. Okay. Now this differential notation, you really see it. You see it when I get into chapter 5. For instance, in chapter 5, we're doing something called an integral. This is the notation for it. And we're going to be integrating 4x dx, which means we're going to be looking for what was the function whose derivative turned out to be 4x. And so we'll go backwards, and the answer to that is going to turn out to be the 2x squared plus some constant. Okay, so that you'll see that notation. See that 4x dx, that differential notation? So you're going to see that a little bit later when we do in chapter 5, when we deal with something called an integral. Okay. All right. So really, it seems almost pointless here. It really is just a matter of the notation. We want to find dy. So you can start by just saying, well, you know that y prime, which is dy dx, here would be found by doing 2/3 times 3 times x to the 2/3 minus 1. And you're doing the derivative with respect to x, so the derivative of x would just have been 1. That's why you don't have anything extra over there. So then you clean it up. 2/3 times 3 would be 2. 2/3 minus 1 would be negative 1/3. Okay, so dy dx equals that. So that means dy would equal 2x to the negative 1/3 times dx. And then if it's a negative exponent, we should rewrite it so that would move to the denominator. And then if it had started with radicals, I might want to write it as radicals, but you could put your answer that way, or you could write it with a cube root of x down there. Okay, so either of those would be what they want. Okay. All right, now let's just do a few more. Really, it's more practice with derivatives, and it's just like that very last step where you just move that dx to the other side is a nice way to think about it. Okay, so the derivative of y with respect to x, on this one, I would first want to think about this like before as a with an exponent, fractional exponent rather than a radical, so that I could use my power rule. So it'd be 1/2 5 minus x third to the negative 1/2, but I got to do the derivative of the inside, which is negative 3x squared. Okay, so that turns out then dy would equal the 1/2 5 minus, that would be in the denominator. Let me go ahead and just look at this whole thing. So it would be negative 3x squared would be on top. Down here I'd have the 2 and the 5 minus x to the third in the denominator with a square root on it. Okay, and that was dy dx. So dy would equal that. Wait, I put my parenthesis in the wrong spot. It was there. Okay. 5 minus x to the third. The parenthesis was around the outside of that. You really almost don't even need it since the cube wasn't on 5 minus x. You could really not even have those once you got the radical in there. So it might be better just to see it like that. Okay. All right. So then at the end, I've got to move. Once I've got that down, I've got to move that dx over to the other side by multiplying it. All right, so it's finding the derivative that's going to be the hardest part. Then you just pull that dx over to the other side. All right, so if I'm going to do the derivative with respect to x, the left side would be dy dx. This is really an x to the 1/2 plus an x to the negative 1/2, isn't it? So I would get 1/2 x to the negative 1/2 when I do the derivative of this, minus, because I brought the negative 1/2 down, so it's minus 1/2 x to the negative 3/2. Okay. All right, so on this one, you might work a little more to clean that up a little bit better. We could try that factoring step we learned earlier. I'm going to pull out the 1/2 and an x to the negative 3/2 and see what's left when I do that. Then here I would need an x, and I would need it to a power to where negative 1/2 was left. So it would just need to be to the first power. And then I took everything out of here, so that would just be -1, wouldn't it? Okay, and that's dy dx still. Okay. So that means down here I have a 2. The x to the first is just x. I have x minus 1 on top. I don't even need the parenthesis. Okay, and then I have x to the 3/2 in the denominator. And it's 3/2, so that means it would be square root of x to the third power. Okay, and then I don't need that so long, so let me shorten that a little bit. And that's, at this point, that's dy dx. So when I change that to differential notation, I'm just going to bring that dx over here. Okay. And then just like before, you might need to use a product rule like we do here. Okay. And you might need to still remember all your sines and cosines like we do on 30 in that example. Okay. So let's do these two, and then I'll post this. And then we'll do the other piece of this is when we're looking at trying to estimate propagated error by using these differentials to do that. I'll show you what I mean by that when we're together in class. All right, so on number 30, I start off by doing the derivative with respect to x on both sides. All right, this right here involves the product rule. So I'm going to do the derivative of the first function. So it'd be e to the negative 5x times the derivative of negative 5x times the cosine 4x as is. Okay, remember that's all part of the cosine there. Okay, then I'm going to add to that the first function as is times the derivative of the second one, and that would be negative sine 4x, and then all of that times the derivative of 4x, which would be 4. Okay, so take a moment to do what you can to clean that up a little bit. So I like to get each term written better, and make sure you don't pull that 4 out of 4x and put it with the 5. That 4x is the input to cosine. It's attached to the cosine. You can't extract the 4 out of that. So this one, if I wrote it with the numerical coefficient out in front, that might help me. And then this is really all together with the that. Then here, this 4 though, see that was after you did the derivative of cosine. You then went back and looked at the derivative of this inside piece right here, and that's where that 4 came from. So it is not tied to the sine. So I am going to put it in front. That would be 4e to the negative 5x. And let me change this to a minus because of this minus right here. So I really have minus 4e to the negative 5x sine of 4x. Okay, so I can't really make this a whole lot better right now, but I did notice there's at least e to the negative 5x that's common, so I could pull that out. All right, so I might do that. If I pulled out the e to the negative 5x, then inside here, maybe I'll go ahead and pull out a negative. Then inside here, I'd have positive 5 cosine 4x. And then I would have, if I pulled out a negative along with it, then wouldn't I have plus 4 sine of 4x? Right, and then I didn't miss anything, so I'm just double checking that I didn't miss anything. So I think I'm okay there so far when I did that. Okay, and that's still dy dx. Okay, all right, so one more thing I might do. Let me see if I can just get a few more lines here. Okay, is maybe move, I don't even know that I would move that down because they had a negative exponent. They left it where it was. I was going to move that e to the negative 5x to the denominator and make it e to the positive 5x. But since this had a negative in it, I think we should be allowed to leave it with a negative in it. So I'm just going to leave it like that. In fact, I would have taken it if you left it right there in terms of the derivative. But I haven't yet changed it into differential notation. So now I'm going to multiply through by the dx. So that means I'm going to take this whole thing. Okay. And I'm going to throw that dx there at the end. Okay. And you could have done it here just put parentheses around all that and throw the dx at the end. All right, so just wanted to get that out of the way because it's really the hard part is doing the derivative. Then all you do is you move that dx to the other side. Okay. All right, one last one. All right, what if we had y equals x sine x? Okay. So we'll start by doing dy dx. This is a product rule problem. Derivative of the first times the second plus the first times the derivative of the second. Okay. And then multiply both sides by dx. So we'll get sine x plus x cosine x dx. And that's what they want. That's the differential notation. All right.